Hello and welcome back to the channel. Today I'm doing something a bit different. This is a presentation about exoplanets. It's kind of an update on what we know about exoplanets, how we find them, and what's going to happen in the future with respect to exoplanets. So let's get started. First of all, what is an exoplanet? The definition that many people use, which is incorrect, is an exoplanet is a planet circling another star. There are also rogue planets, as we'll see, planets that are unassociated with any stars. Another more subtle reason why we can't say an exoplanet is a planet orbiting another star is we have found exoplanets orbiting pairs and even triplets of stars. It's difficult to find exoplanets. Consider that even the brightest of the exoplanets reflect less than 1% of their star's light. They're very difficult, although not quite impossible, to image directly, as we'll see. So mostly we rely on indirect methods to find exoplanets. As of October of 2024, we've confirmed 7,337 exoplanets. And some of the methods we use to find them are the wobble method, which has found 187, the Doppler method, which has found 1,276, the transit method, which is the most successful method, gravitational microlensing, direct imaging, pulsar timing, transit timing variation, kinematic, polarimetry, and aliens hand us a map, which has not worked yet. Let's talk about the wobble method first. Stars normally move in a straight line, but if they are tugged upon by an exoplanet, they will appear to wobble as they move. It's very subtle. It's very difficult to detect minute changes in star positions, especially for distant stars. Plus, you need to have a massive enough exoplanet to affect the orbit of the planet itself. The wobble method is also called the astrometry method. Some of the advantages are you can accurately provide the mass of the planet, and you can find exoplanets around many stars at the same time, but it requires extremely high accuracy, takes a long time to get a measurement, does not work well for distant stars because their apparent motion is very reduced. It also does not work well for small mass planets, and it generally requires a space-based telescope. The Doppler method relies upon the likelihood that the star and the planet line up exactly with our line of sight. Wavelengths of light are alternately squeezed and then stretched as the star moves closer and then further away. This was the primary method for finding exoplanets prior to the Kepler and TESS missions. Here's an illustration that shows that in a different way. Note that it only tells you the component of velocity in your direction, which can lead to an underestimating of the mass of the planet. The one advantage of the Doppler method is it can work on very distant stars. The most popular method for finding exoplanets is the transit method. And many of us are familiar with the transit method as it pertains to our own solar system. As shown here, you could see Mercury or Venus crossing in front of the Sun. Well, imagine that at a very distant scale, where a planet may cross in front of a distant star, assuming they line up correctly. This is kind of how it might look. Now, you can imagine that the amount of light which is reduced when the planet goes in front of the star is extremely small. In fact, it's normally less than 1/2 of 1%. The analogy I like to use is imagine you're out in the desert somewhere dark, and there's a distant car headlight and an ant is crawling across the headlight. If you had a sensitive enough light meter, you could detect that the ant was crawling across the headlight, but it's very difficult to do. These also require a correct orientation of the planet with the star. If the planet is circling around the star and we don't see it cross in front of the star, then this method does not work, which means that for over 99% of stars, this method will not work. Here's an illustration of what that might look like. at high scale. Obviously, it's much smaller than that. I'd like to draw your attention to the graph on the right. Note that in this example, the brightness at worst decreases by about 0.5%. These illustrations are far more exaggerated compared to what's normally seen. So there are a lot of advantages of the transit method. It allows you to determine the size of the exoplanet. It's the most effective and sensitive method known. When you combine that with radial velocity data, you can deduce mass and density of the planet. Atmospheric absorption spectrum tells you about the atmosphere and the temperature. It's very efficient. You can check the sky and see many stars simultaneously and check them for transits. But the exoplanet orbit, as I mentioned earlier, must align with our line of sight, and you need to be looking when the transit occurs. So imagine planets like Saturn, Jupiter, Uranus, Neptune, which take many years to cross in front of their star. They would be very difficult to find. We'd have to be looking at exactly the right time to see them, and given that you need to have several transits to be sure that you've actually found an exoplanet, one transit, even if it was caught for a planet that has a 50-year orbit around its star, it's going to make it very difficult for you to verify that again. So the Kepler mission from 2009 to 2013 searched for the presence of exoplanets. And you can see here the Milky Way with the constellation of Cygnus, or the Northern Cross, and you can see where Kepler looked in the sky to find exoplanets. Here's an example of a Kepler light curve. Note the light is dimming by much less than 1%. One thing that's really cool about the transit method is now that we have the James Webb Space Telescope, we know that during a transit, if the planet has an atmosphere, the atmosphere can absorb certain wavelengths of light, and this gives us a fingerprint telling us which elements are in the atmosphere. So by looking at the spectrum of the star before and during the transit, we can then subtract the spectrum of the star from the composite spectrum and deduce what is in the atmosphere of the planet, which potentially could help us find signs of life. The mission was completed originally in 2012, but the Kepler-2 mission began in 2013, and the spacecraft finally ran out of fuel in 2018, and it was officially retired exactly 388 days from Johann Kepler's death in 1630. And you can see some of the statistics for the mission. It was a very successful mission. So an interesting side thought is, what if aliens use the transit method to try to find us? So just as we can use the transit method to find other planets, an alien looking at us in the right orientation could find us as well. And we've figured out which stars are aligned to see the Earth when it crosses in front of our sun. So what we could do is we could shoot a laser beam at the other star at the exact moment when our planet would be transiting in front of our star to fill in the gap in light caused by an Earth transit. It's actually a very feasible technology and would require lasers which are readily available. There are about 82 stars within about 3,500 light years from Earth where potential inhabitants could see Earth cross in front of our sun. They would have to be watching and catch a short 3 to 6 hour window every year to see us. But we could hide if we wanted to. The next method is microlensing, and this is probably the most complex method. Light from a distant star is bent and focused by gravity as a planet passes between the star and the Earth. Occasionally, a star lines up perfectly in front of a more distant star. The momentary alignment magnifies and brightens the light from the background star, an effect called gravitational microlensing. You can see in the illustration the second sharp increase in brightness caused by a planet. This method is very good for finding low-mass exoplanets, which are hard to do. It's also very good for very distant exoplanets, and you can look at large areas of the sky simultaneously. But you can't use it twice on the same exoplanet. They're very unpredictable. And because most findings are very far away, you can't use other methods to verify them. So in this illustration, you can see where most of the exoplanets have been found in red. The circular part is the TESS mission, and the little beam is the Kepler mission, and then the little white dots give you some examples of microlensing exoplanets we have found. It's also possible to have extragalactic microlensing. So quasar microlensing creates Einstein rings. You can study emissions near the accretion disk of a quasar supermassive black hole, and about 2,000 rogue planets have been found this way. All right, now we'll talk about direct imaging. Direct imaging is difficult because the star is so bright in comparison to the light from the adjacent planet. You need to remove the overwhelming glare from these stars. Here are some photographs of some directly imaged planets. So some advantages of direct imaging: you can use visible or UV light. It's the only known method which is direct, but it must be relatively close, and the planet must usually be large and far from the host star so we can separate its light from the star's light. And it can be confused with a brown dwarf binary, and you don't usually get sharp images. So there's a lot of challenges with this method, but we have found planets this way. Pulsar timing is the next method. So what is a pulsar? It's a rapidly rotating neutron star, and these emit extremely regular radio waves. But if you have a planet circling a pulsar, the tug of the planet will affect the timing of the pulses, and you can use calculations to reveal the size and shape of the orbit of the exoplanet. It's a very sensitive method, and you can deduce a lot of information about the exoplanet, but pulsars are rare, and also life is unlikely on such exoplanets. To round out the number of methods, you have the transit timing variation method, you have the kinematic method, and you have the polarimetry method. And you can read about those here. Finally, a bit tongue-in-cheek, there was a famous UFO story called the Betty and Barney Hill episode, and Betty Hill, under hypnosis, drew a map that she said she saw inside the spacecraft when she was abducted. And some people have taken that map that she'd drawn and found a rough analogy to how the stars might look in the sky if you were based on Zeta Reticuli. So maybe one day aliens will land and just give us a map to the exoplanets. But in the meantime, we have to use science. So how are exoplanets classified? You have terrestrial planets, of rocky composition type planets, and you have subterran, terran, super-Earths, and lava worlds. Larger than that, you have gas giant planets, you've got Neptunian planets, ice giants, and Jovian planets. One thing that was interesting I learned is that Earth is not really the ideal size and mass for life. Scientists believe that Earth is actually on the small side when you look at optimal planet sizes for life to survive and flourish. Super-Earths have higher gravity, which helps them hang on to their atmospheres and extend the Goldilocks zone. It also makes for a smoother planet, causing water to pool in shallow areas around islands rather than in deep oceans and high continents. The most biologically active areas on our planet are found around islands and shallow seas. The Kepler Space Telescope has found over 1,000 of these super-Earths searching just a tiny portion of the sky, some of which are illustrated here. Here's a graph which shows exoplanet populations and which ones have been found by which methods. Now let's talk about some interesting exoplanets. 55 Cancri is a Terran planet which is so close to its host star that the surface is molten. Hot Neptunes are Neptune-sized exoplanets orbiting in or closer than the Goldilocks zone. Some of these could be enormous water worlds. 51 Pegasi b was the first exoplanet discovered in 1995. It's a hot Jupiter. It's likely being vaporized by its host star. Tau Ceti is the closest Sun-like star to our own. It's 12 light-years away in the constellation of Cetus. In August of 2017, advances in the wobble method allowed scientists to confirm it has 2 super-Earths, both of which are within the Goldilocks zone of the star. So just imagine that. The closest Sun-like star to our own has 2 super-Earths, both in the habitable zone. You can also have a binary star with stable exoplanets. We found 9 of these. These are technically called circumbinary planets. One of those is Kepler 16b. Here's an animation illustration of a triple star with a stable exoplanet. We found 40 of these. Kepler 22b is sometimes called New Earth. It's 600 light-years away, sitting in the Goldilocks zone of its star, with an average surface temperature estimated to be 72 Fahrenheit. It's believed to have a rocky core and abundant liquid water. It's a super-Earth. This is one of the youngest exoplanets ever discovered, estimated to be just 5 million years old. It's about twice the size of Jupiter. Then here's the oldest known exoplanet, so-called Methuselah. It's orbiting a pair of white dwarf stars, 12,400 light-years away in Scorpius. At 12.7 years old, it tops the age scales. It's about 2.5 times the mass of Jupiter. And at first there was some debate about whether it might be a brown dwarf, but we've since determined it's a large Jupiter. GJ 504b is a pink planet which is still glowing from the heat of its formation. It's believed to be very young. Barnard's star is the second closest star system to our Sun, and it has the highest proper motion of any star. We recently used the wobble method to discover a super-Earth orbiting Barnard's star every 233 days, but doesn't get much light from its star because the star is so faint. We also have found the first exomoon. Exomoons, of course, are moons that circle exoplanets. Proxima b is the first exoplanet found around Proxima Centauri, the closest star to our Sun. Here's an illustration that shows a little bit about how that might work and how it might look. Thanks to the University of Puerto Rico at Arecibo. Recently, we've discovered rogue planets unassociated with any star. Current models of planetary formation suggest planets can be flung out of a star's gravitational pull during the early formation of a solar system. Some scientists speculate there could be over 100 billion of these rogue planets in the Milky Way. They're all found using the microlensing technique, where we know there is no host star. Let's talk for a few minutes about exoplanet missions. The Spitzer Space Telescope was launched in 2003, and it has been used to find exoplanets. And it's optimized to find protoplanetary disks, brown dwarfs, and infrared galaxies, and also has found exoplanets. Here's a short animation talking about TRAPPIST-1, which is probably the most successful discovery of Spitzer. TRAPPIST-1 is a 19th magnitude red dwarf about 39 light years away, found near the ecliptic by Theta Aquarii.
Imagine a place with not one, not two, but 7 Earth-sized planets all orbiting a single star. It's not just science fiction thanks to a new discovery by NASA's Spitzer Space Telescope. TRAPPIST-1, an ultra-cool dwarf star just under 40 light-years away, plays host to this incredible collection of planets. It is likely most, if not all, of these planets perpetually keep one face pointed toward their star, a phenomenon called tidal locking. This would create large temperature gradients across their surfaces and offer the possibility that liquid water could exist on any of them under the right conditions. Moreover, if you could stand on the surface of one of these worlds and look up at your neighboring planets in the sky, they would at times appear larger than our moon looks to us. That's because TRAPPIST-1 is only a little bigger than Jupiter, and the TRAPPIST-1 planets orbit only a little farther apart than Jupiter's moons. Interplanetary trips here would be measured in days, not months or years like in our solar system. For now, we can only speculate what these exoplanets might be like, as we still know relatively little about them. Upcoming missions like the James Webb Space Telescope will study the TRAPPIST-1 system in greater detail and uncover more clues about the atmospheres and compositions of these 7 Earth-sized worlds.
All right, then we have the Transiting Exoplanet Survey Satellite, which is now in its 2nd extended mission. And unlike the Kepler space mission, TESS was optimized to find exoplanets close to the Earth. You can see the illustration here showing the difference in where TESS was looking in kind of green and where Kepler is looking shown in yellow. And this is an illustration showing which exoplanets have been found by which method, which satellite. The European Space Agency launched the Cheops mission. It's the Characterizing Exoplanet Satellite. And it's also been looking for exoplanets and has helped find them. Then we have the James Webb Space Telescope, which has been tremendously successful. It's actually exceeding most of the performance parameters they expected to get from the James Webb, and it's going to be able to help us characterize the atmospheres of exoplanets. So what's happening is there are systems like TESS which make an initial discovery, and then they use ground-based telescopes to examine the initial discoveries and filter which ones might be of most interest for James Webb. And then after that filter, James Webb looks at the remainder of the ones which are highest priority, and then we can see whether we could find interesting things in the atmospheres of these exoplanets. Then we have the Nancy Grace Roman Telescope, formerly called W-FIRST. That should be launching in about 5 years, and it will have 100 times Hubble's field of view, and it should be able to study dark energy and find exoplanets via gravitational lensing. We have the ESA Plato mission launching in 2026, composed of a network of 120 millimeter refractors. There is the Ariel mission planned for 2028, also going to be positioned at the L2 Lagrange point. And a point about exoplanets it's good to make is that some people assume you have to have a small rocky planet to find life. Well, not necessarily true. It's quite possible to have habitable Earth-like moons in orbit around gas giants in the habitable zone. This was the concept behind Pandora in the movie Avatar. We've identified hundreds of gas giant exoplanets orbiting in the habitable zones of their host stars, which could very much host moons like this. In 2015, astronomers deduced there could be 60 billion Earth-sized planets orbiting in the Goldilocks zones within our galaxy. Recently, we've realized that moons of larger planets could also support life, just like Enceladus and Europa in our own solar system may support life. So now there could be over 100 billion locations just in the Milky Way. So key takeaways from this presentation include super-Earths and mini-Neptunes are the most abundant planets known to date in our galaxy. At least 50% of stars have a close-in exoplanet larger than Earth, and we believe that most stars have planets as a rule. At least 10% of the stars we've looked at have a Jupiter-type planet. Our upcoming missions are going to have increased resolution and should significantly increase the number and understanding of exoplanets. We also have a good chance of detecting evidence of life if it exists on exoplanets in the habitable zones. And there are over 7,000 confirmed exoplanets as of October of 2024. If you want to learn more, here are some websites you can check out. Thanks for watching.